Hi everyone, I'm Xuheng from Columbia, and today I'm presenting Spoq, Scaling Machine-Checkable System Verification in Coq. And this is a joint work with Xuheng, Qiang, Ronghui, and Jason Nieh. So everybody wants to have absolutely correct systems. We want operating systems that never crashes. We want file systems that never lose our data. And we want cloud hypervisors that never leaks our secret. And there is a promising way to achieve that is to formally verify those systems. And means that we use math to prove that the system implementation satisfies our expectations, formalized as specification. And the typical workflow to do that is to first translate the source code into some formal representation, and we prove the formal representation satisfy our specification. And this process is so-called functional correctness proof. And functional correctness proof is important since it guarantees the system implementation satisfies the specification. And that means if you further prove that the specification satisfies some higher level properties such as security, the properties will also hold on your implementation. But functional correctness proof is also the most challenging part in system verification. And even the first step is already very challenging. That's because system software are usually implemented with many non-standard language features, such as compiler derivatives and statement expressions. Most verification tools do not support any of them. For example, CLI-Gen is a widely used tool to formalize C code into Coq proof assistant. But when we test it on 5 open source projects, it fails to pass any of them. And over 99% of the Linux kernel are failed due to these unsupported language features. So this is why people need to retrofit the code to remove those language features before verifying it. And it is actually a big problem because verifying a simplified code does not give any correctness guarantee to the original code, since retrofitting may introduce inconsistency. We do find bugs from the original code, even though the simplified code is verified. And okay, then the next challenge is still the huge proof effort. Let's see this system verification work published in recent years. And there's one thing in common. The proof effort is so huge. For each line of source code, we may need write 8 lines of proof. And that's why we create Spoq, a new verification framework that can verify C system code and make it easier to use Coq in system verification. We try to solve both challenges with Spoq. And first, rather than directly formalizing the source code, we leverage Qiang to translate the system code to LLVM IR, then formalize the LLVM IR code. And with a rule-based reconstruction algorithm, we can support over 99% of the code from Linux kernel. And Spoq also greatly reduced the manual proof effort by automating the spec definition and the proof. And in our test, Spoq reduced about 80% manual proof effort. And let me first talk about the first part. We choose to compile the source code into LLVM IR instead of manually retrofit it, because LLVM IR won't be inconsistent with the source code. And LLVM IR has clean syntax and semantics, which effectively eliminating the need to support complex language features from the rest of the verification framework. And however, let's see the example code in LLVM IR. And the code is organized as basic blocks with jumps without any proof structures. Like there are 4 blocks in the example, the entry, P, Q, and the return. And for instance, the entry block eventually jumps to P or Q based on the condition C, and the P blocks jumps to return or Q, and etc. The lack of explicit program structure such as if statement and loops makes verification very hard. So we introduced a rule-based reconstruction algorithm to generate our formal representation with program structure. To do that, we first convert the IR code into a control flow graph, where each box is a code block and each arrow is a jump. And then we keep applying the rules to generate the structured formal representation. And to see how it works, we keep applying the rules on the left side, and we can find that the graph is becoming simpler through each iteration. Right? Yeah. When there is only 1 node left, the algorithm is complete, and we successfully construct the structured formal representation from the source code. And then let's talk about how Spoq automates the spec definition and the proof. So now we have a formal representation of the source code. We need to define a specification to model its high-level behavior. And we need to prove that the code indeed satisfies the specification. And obviously, there is a huge gap between the code and the specification, and the proof will be long and tedious. So here, this is what Spoq does, is trying to generate a sequence of intermediate specification with best effort and generate proof showing that all those intermediate specifications are equivalent to the code so that it can reduce the gap between the code and the specification. And then, instead of directly proving the code satisfying the specification, user now can prove the intermediate specification satisfy their own specification. That will be much easier. And actually, in many cases, the intermediate specification is pretty close to users' expectation. So users even don't need to define their own specification. Just use what Spoq generated. And then let's see how to generate those intermediate specification. I'll use the example C code to demonstrate. The code contains a branch, and in the then branch, we swap the 2 variables, x and y, and in the else branch, we do x plus plus and y minus y minus. And eventually, we return x plus y. So actually, the huge if statement does nothing, has no effect. And I will show how Spoq automatically reduces the code into a simplest specification. But let's start from generating the first specification from the code. Assuming we already have the formal representation here, since the formal representation is well structured, the program logic actually forms a tree structure as presented here. And to generate the spec for it, we simply traverse the tree and aggregate each small step of the code to form a big step, like this. Like we start traversing the tree and collect the behavior of the code. And when we enter in an if statement, we create a template step for it. And we fill the details, and we aggregate the behavior of the small steps. Okay, and then we generate an initial specification with exactly the same computation as the code. And at the meantime, Spoq also automatically generates a proof showing that the spec is indeed the aggregation of each step of the code. And Spoq also handles the case that code contains loops, and feel free to read our paper for more details. Then, once we got an initial spec, the Spoq can apply a sequence of rules to simplify it. And the Spoq also generates proofs showing that the simplification to the specification does not change its behavior. For example, the Spoq can do syntactic transformation like eliminating the then branch, eliminating the let statement by replacing the variable with its definition. Yeah, and then Spoq can also simplify math expressions using SMT solvers like Z3. All the transformations proposed by Z3 will be recorded as proof hints and will be used in constructing the proofs. And Z3 can also tell us the then branch and the else branch are actually equal, so we can further eliminate one of them. And so as we can see, Spoq can generate quite simple specification from the code, which greatly simplify the manual proof. Then to evaluate Spoq, we first compare Spoq with SelectGen on formalizing system code. We tested them on 5 open source projects, and the result shows that Spoq successfully formalized over 99% of the code for all the projects, while SelectGen fails on large portion of each project. And we have also used the Spoq to verify SE-KVM. SE-KVM is a multiprocessor KVM hypervisor. And previously, we have verified a simplified version of SE-KVM with around 34,000 lines of manual proof. And recently, we port SE-KVM to Raspberry Pi, and we changed the implementation a bit, and then the previous proofs are broken. So we redo the proof with Spoq. And this time, we successfully directly verified the original source code of SE-KVM with about 7,000 lines of manual proof, much less than the previous proof effort. And the total manual proof effort actually reduced like 79%, which shows the effectiveness of Spoq. And in summary, we create a new verification framework, Spoq, that enables formalizing complex system code and reduce the huge proof effort by automating the spec generation and spec definition and proof. And thank you for listening, and live long and prosper.